Yes, so I'm going to present our work that explores how we can utilize the flexibility of upcoming flexible packet processing hardware to implement network resource protocols inside data center networks. Again, this is a joint work with several of my colleagues over various locations. Let me start off by defining what I mean by flexibility here. And by flexible, I'm referring to programmable switching circuits that can process packets at line rate, which today is anywhere between 3 to 6 terabits per second. I'm not referring to software or FPGA-based routers that have general purpose cores sitting on them and process packets 1 or 2 orders of magnitude slower than these circuits. And they're able to achieve this high performance by using a restricted computational model, such as the reconfiguration match+action table, which looks very similar to OpenFlow. And this flexibility is very attractive because it allows data center operators to reprogram or reconfigure these switches after they have been deployed. And so they can implement or prototype new protocols without waiting for new hardware to come out, which would then implement these standardized protocols in silicon. And they can also reallocate various switch resources to the functionality depending on their workload or requirements, such as either L2 MAC learning or L3 routing or ACLs and so on. And recent research has shown that this flexibility comes at a fairly minimal and reasonable hardware cost compared to these fixed function ASICs that implement the protocols in the silicon. And you can see several manufacturers coming up with their own versions of these switches, such as Cavium XPlant or Barefoot Tofino. And in the rest of this talk, I'll be referring to these as like flexible switches. Let's take a look at how this flexibility is achieved in practice using a reconfiguration match+action table. The first thing that happens when a packet stream is processed is parsing. And a hardware programmable parser breaks down the byte stream into different individual protocol header layers. In this case, it could be Ethernet, IPv4, which could be then a TCP or a UDP packet. And if you want to implement your own fancy protocol, you could reprogram the parser to identify this new field and identify its headers. Once these headers are extracted, they're passed on to a series of match+action tables, each of which matches or looks up one of these fields and performs some action. Typically, these stages have some TCAM for performing arbitrary wildcard matches, some amount of SRAM for implementing exact or longest prefix match lookups, and some amount of general purpose registers for maintaining counters or meters that persist state across packets. Finally, there are some amount of ALUs that can be used to modify the headers or update the state within these stages. After modification, so the first three components essentially are the matching primitive, and the last one is essentially the action primitive. And once these headers are modified, they are passed on to subsequent stages until you figure out where this packet is destined and you enqueue it in the right port or right egress queue. So you can imagine doing something simple as when a packet comes in, you look at the destination MAC address to figure out the outgoing port, assign it to the egress port, and then say if you want to maintain a count of how many packets are you seeing from a certain IP, you can increment the counter to do that. And this flexibility is amazing. And this flexibility also doesn't come for free. Just like any other line rate switch, these switches also have to deal with certain restrictions because they have to process packets at 1 billion packets per second at like line rate. And the first thing is they're able to do so by having some limited processing primitives, such as just addition, subtraction, or simple bit shifts, which means you cannot perform arbitrary computation on these switches, such as multiplication, division, or floating point operations. The stateful memory available on these switches is also constrained, which means given that these top-of-the-rack switches handle up to 100,000 flows, you cannot maintain significant per-flow state on these switches. Finally, there is a limited number of stages and a limited number of amount of data moves across these stages, which imposes a limit on the total amount of computation or manipulation you can do per packet. So what is this limited flexibility good for, and what can we do on these switches? They are great for implementing traditional network protocols such as custom routing or tunneling similar to VXLAN or MPLS. And most of these are simple packet level transformations that involve static table lookup and simple header rewrites. Can we do some more complex things with these switches? What about some non-traditional network protocols that require even richer support from the network? And there have been several such protocols proposed in the past, several by people in this room, that require active network elements. By which I mean they need to maintain persistent and mutable state at these switches to perform some cross-packet transformations, or they require implementing some sort of state machine functionality to periodically update the state at these switches. And these protocols solve a broad class of challenging network problems, ranging from congestion control to load balancing, or even fairness to QoS scheduling. So can we finally start implementing some of these really nice protocols on these flexible switches? And since this is an NSDI talk, the answer is going to be yes. And the key idea is we are going to use some approximations to overcome some of the hardware limitations on these switches. So in the rest of this talk, taking RCP as a running example, I will showcase our approach where we analyze several protocols to determine both their functional requirements, computational requirements, and even storage requirements. And in process, we come up with a library of building blocks or generic modules that approximate some of these network functions. And again, the key idea will be we are going to use some approximation technique to make it feasible to realize these modules onto these flexible switches. Finally, I'll touch upon some evaluation, which shows whether our approximations are accurate enough or not, and they're effective or not. So let's take a look at RCP. It's a very simple congestion control scheme that relies on explicit feedback from the network. Every switch in the network contains a fair share rate that it assigns to every traversing flow. Every packet contains an RCP header, which contains the rate field, which is initialized by the sender to its desired rate. And as the packet goes through the network, every switch updates the rate inside the packet if its own rate is lower than the one in the packet. So here it would be modified to 25, and as it goes to 20. And once the receiver acts back the rate to the sender, it can start sending at the bottleneck capacity within a single RTT. And this is really nice because, especially for short flows, because TCP takes multiple RTTs to achieve this. And the original RCP algorithm computes the rate as follows, where the new rate is equal to the old rate plus some factor of spare capacity at the link, minus some factor of the persistent queuing at the link, divided over the number of flows traversing that link. And the intuition here is, if you have a lot of spare capacity left, you would increase the rate assigned to every flow to make sure that the link utilization is high. And if you have a lot of persistent queuing, you would decrease the rate until you dissipate the queue, essentially. So let's look at how we can implement this on these flexible switches. First, we need a way to measure the link utilization and the queue lengths. And this is fairly straightforward because these switches already have counters for this purpose. We only need to be able to break it down into control intervals so that we can calculate this rate. Next, we need to be able to perform some multiplication and division. And this is slightly difficult because if you recall, the processing primitives on these switches is very limited. And we can't do multiplication and division on the data plane. But in the paper, we show how we can approximate this using either bit shifts or log table lookups to a fairly good accuracy. Finally, we need to estimate the number of ongoing flows. And this is fairly challenging if the number of flows is really large and we cannot maintain per flow state. So we come up with a generic module that allows us to estimate the number of unique elements in a packet stream. And we call it the Cardinality estimator, which we are again going to use for RCP to count the number of unique flows traversing the switch. And here we extend an approach from streaming algorithms, and it works as follows. Given a packet stream, for each element, we are going to take the hash of the 5 tuple of the packet and count the number of leading 0 in the hash. So in this case, it's 2. And as we process more packets, we are going to keep track of the largest number of leading zeros we have seen so far in any of the hashes. So if the next packet has a hash like this, we would update the maximum leading zeros to 4, and so on. And the nice, beautiful thing about this algorithm is that the estimate for the number of unique elements is simply 2 to the power m. In this case, would be 16. Right? And this is really attractive because it maintains very little amount of state, essentially a single counter for the maximum number of reading zeros. And it requires a single operation, which is exponentiation of 2, which can be easily done by bit shift. And as you might have noticed, this has a couple of issues. The estimate is fairly coarse-grained, and it exhibits very high variation, especially if you have very few elements in the packet stream. So we are going to solve this by splitting the input stream into multiple buckets, such that each unique element goes into a unique bucket. And then we are going to maintain separate estimates of each of these buckets, and then finally average and aggregate across all these buckets. And this gives a fairly good estimate with a low variation. And if we happen to have very few elements, a lot of these buckets will be empty, so we revert to something simple as Bloom filter counting, which is more accurate at low cardinalities. And to give an idea of how well this works, we can estimate number of flows to within 5% error using just 1 kilobyte of memory for up to 100,000 flows. So using this building block, we can implement RCP on these switches. And we did a similar exercise for several other protocols that you can look at in the paper. And the building blocks we came up with are general enough that can be reused across several protocols, such as the cardinality block I just talked about is also used in CVol to estimate how many tenant VMs are traversing through a particular switch, or in case of SNOT, to detect how many different distinct IPs are talking to a particular port, and so on. So I'll describe one more building block in this talk, which is how to maintain approximate flow timestamps. And you can imagine this being useful for implementing Flowlet routing for, say, CONGA or Hula and so on. So let's take a look at how that works. Again, so we are going to use a custom sketch, which is an approximate data structure that stores timestamps and per flow state. And this is inspired from the countmin sketch data structure that stores simply counters. A sketch is nothing but simply a two-dimensional matrix with n columns and r rows. And for each packet that comes in, we are again going to take r separate hash functions and update the cell or column corresponding to the hash modulo n. So in this case, if we have 4 rows, we are going to update these 4 cells. And this is again really attractive for these flexible switches because it only requires r lookups or memory updates, and it can maintain approximate flow state in sublinear space, which is really nice. So let's take a look how we can implement Flowlet routing using approximate flow timestamps. And for simplicity, let's assume we have only 2 rows. Each of our cells is now going to contain a tuple of timestamp and a route ID. And let's say at t equal to 20, packet 1 comes along and it hashes to these 2 cells. Let's take a look at the flow timestamps to figure out whether this flowlet is live or not. And we consider a flowlet to be live if all the cell timestamps are within the configured timeout. Say, let's assume it's 10 in this case. For this packet, the timeouts come up to 20, so we realize this is a new flowlet, and it's not live currently. We are going to update the timestamp to reflect the fact that this flow is now live, and we update the timestamp in the sketch. And since this is a new flowlet, we get to choose its route ID, which port to assign or to assign it to. And let's say we choose route ID 5, either by just random ECMP hopping or by choosing the least loaded port and so on. And the way we are going to persist this information in this state, in this sketch, is that the sum of all cell route IDs is equal to the desired route ID, in this case 5. So we can do something as, let's persist 2 plus 3 equal to 5 in the sketch. Right? Next, let's say a packet of an orange flow comes at t equal to 25. Again, we look at the timestamp and hashes to these 2 cells, and there's a collision in the second row. Let's again try to figure out whether this flowlet is live or not. The timeouts are 25 and 5, and one of the cells is non-live, which tells us that this flowlet is not live. So we can then update the timestamps in the sketch to make it live, and we get to choose the new route ID for it. However, in this case, we are only allowed to rewrite the non-live cells in the sketch to reflect this new route ID. And in this case, we'd have to do 5 plus 3 equal to 8, and we only modify the top right cell. Finally, if a packet of the blue flow comes along again within the Flowlet timeout, we'll realize that this is a live Flowlet because all the timestamps are within 10. And we can, since this is a live Flowlet, we cannot reroute it to a new ID. We would have to look up the current route ID, which we can find out by just adding the two cells values, which is 2 plus 3 in this case. And this method is always safe, and it maintains the livelet of flows in the fact that it will never reroute an active flowlet. And this is required for correctness, essentially. So let's move on to some evaluation to figure out whether all I described right now works in practice or not. And I'm going to answer these questions. Do the approximations work on real hardware? Can we get the benefits on real hardware? And we do so by implementing and evaluating RCP on a real hardware, a Cavium expand switch. And since we are doing so much approximation, does it have a significant impact on these protocols themselves? And so we compared the original and the approximated versions using NSDI simulations. And finally, how much extra resources do we consume when implementing these approximations? And so we are going to measure the resource usage on top of a P4 switch. So let's look at the RCP implementation on a Cavium switch, which we built using the building blocks I described. And we tested it on a small factory topology using a simple all-to-all communication workload. And I'm going to show you the flow completion times for various flow sizes with the flow completion time on the y-axis. And so lower is better. And we are going to compare against the default Linux TCP implementation shown in blue and RCP in orange. And as expected, you can see RCP gives great performance benefit across various flow sizes. And this is great, not because RCP did better than TCP, but because almost 10 years after, or a decade after RCP was proposed, we finally have a hardware implementation that runs at line rate. And we are in the process of implementing it on the Barefoot Tofino switch that runs at an even higher 6.5 terabits per second. Next, let's look at the impact of approximation on these protocols. And for this, we are going to implement two congestion control schemes, RCP and XCP, both the original and the approximate versions in NS3. And again, we run it on a fairly large factory topology and measure flow completion times to see if there is significant deviation. So this graph shows the flow completion time, the CDF of flow completion time for both the solid lines representing the original protocols and the dashed line representing the approximate versions of these protocols. And as you can see, there is almost no difference. It's barely visible on this graph between the original and the approximate versions. And this shouldn't be very surprising because these protocols are designed to be robust and stable under a wide range of network conditions. So as long as our approximations don't have any systematic or inherent bias in them, we'd always converge to the desired protocol performance, essentially. Lastly, let's see how much extra resources we use when implementing these approximate protocols. So we implemented, again, a bunch of these protocols in P4 on top of an open source switch. And we compiled this P4 code on top of a real switch based on the Tofino hardware model. And the switch essentially has most of the common features you would expect from a top-of-the-rack switch, such as L2 MAC learning, L3 routing, link aggregation groups, ECMP, and so on. And the table shows which of these resources are utilized and how much space do they take, such as the packet header vector in how many bits, the SRAM, how much memory blocks we're using, and how many ALU instructions, and so on. And as you can see, most of these numbers are fairly minimal, from between 5 to 10%, which is great because we can now implement a lot of these nice protocols without a lot of overhead. XCP requires a little more ALU operations because it does more per packet computation, and CONGA requires slightly more amount of memory because it maintains per link utilization levels, essentially. So in summary, in this work, we show how we can use programmable switches to implement a broad class of non-traditional protocols that require rich support from the network. And we do so by overcoming the hardware constraints associated with these switches by using approximation techniques. We show that these approximations are both effective and accurate by demonstrating benefits on real hardware, as well as running simulations to show that the protocol behavior is largely unaffected. And as ongoing work, we are looking at designing new protocols that are tailored to these flexible switches so that we don't have to go through this whole exercise. With that, I'm ready to take any questions.
Yuliang from Yale. So this is a network. I like it. So during your study of so many network applications, what are the features that are not yet currently supported by the programmable switches, but you hope that you could have?
Right. So one such feature is related to, I think, queuing, right? Because if you have to operate these switches at line rate, the queuing that happens on these switches is just FIFO queuing. But a lot of protocols require some sort of a priority queue in there, or maintaining state in a priority heap, essentially, in a sorted manner. And that is fairly expensive to implement on these hardware right now. There is a work recently at SIGCOMM which proposes a way to do that. And if we have that available, I think we can expand the set of protocols to an even larger set.
I see. Thank you.
Hello, nice work. Mehrdad Moradi from University of Michigan. I guess in order to improve the performance of this stateful switching architecture, one way is to compress the memory footprint, which is actually what you did. Did you also try to reduce the number of memory accesses in order to increase the performance? Because it might be the case that multiple packets wants to access the same registers in order to...
Correct. So I think that's what these pipelines are great for, because they split. Different architectures might do it in different ways. But if you have a pipeline of these stages, you can split the memory into different stages, and then they can happen in parallel.
So did you do in your design?
For this work, we specifically did not do it for any other protocols, but that is definitely a case. If a protocol has to update the same state multiple times, then we'll have to limit it using some way.
And the other thing was that a few times you mentioned that it is not possible to implement new switch actions like multiplication in these P4 switches. But I guess most of these P4 switches, like Netronom, P4 NICs, and Barefoot switches, you can actually define new primitive actions and develop these things in C++ or C, right?
Right.
And I guess my last question is that why did you pick NS3 for evaluation? Because given there is the software switch of the P4 available on P4 board.
Right. For NS3, I think it was just simpler because we had the original implementation ready in NS3, and then we just compared it with our own approx version. If we had to implement it in P4 software switch, we'd still have to express XCP in P4, which would again involve some approximation, right? We couldn't implement the original XCP in P4.
But you had the P4 implementation for hardware switches, right?
Seems like a good discussion for something.
Yeah, we can take it offline. But essentially, even in P4, we cannot implement these protocols as it is exactly, because we'll have to do with these. Because P4 itself is a restricted model.
Okay, thank you.
Let's take one last question. Sure.
Hi, Vishal Srivastav, Cornell. Nice work. My question was, so your work seems very similar to the domino work which was proposed in SIGCOMM. So they have this concept of building blocks.
Correct.
So I was wondering, how does your work contrast with domino?
Right. So to sort of recap, domino is a work at SIGCOMM which basically proposes a high-level language to essentially express the same sort of protocols on top of these flexible switches. And I think the key difference is in domino, if there is a protocol that cannot be expressed on this limited hardware, the compiler will just throw back saying, well, I can't do this because the programmability of the elements is not expressive enough. Whereas in our case, we basically try to figure out what is causing that restriction and try to fix that by approximation. So you can imagine this being orthogonal to domino, where we propose building blocks that can fit into domino that would approximate some function or a block basically used by domino.
Cool. So, thank you.
With that, let's thank Naveen.